Welcome back, geology fans. Throughout this series on sedimentary rocks, I have mentioned various environments of deposition, but it is of use for us to summarize these environments before continuing on to our final rock type. We will use this model of terrestrial to marine environments to describe the various features we will see in each, and we will progress from the higher to lower elevation settings. Our high elevations are dominated by the erosional agents of ice and gravity. Rockfall from the face of a cliff produces a steep slope of poorly sorted and angular rock fragments that form a deposit we call talus, or scree. Landslides and gravity-driven deposits accumulating at the base of hillsides have a more fine-grained material in it, ranging often from silt to those larger rock fragments which still show angularity and poor sorting. Such gravity-eroded deposits are called colluvium. Glaciers are also encountered at high elevations and high latitudes. Glacial material starts as subangular, poorly sorted sediment resulting in glacial till. Talus, or scree, colluvium, and till are all poorly sorted, but as long as these deposits are exposed at the surface, they can be acted on by the other two erosional agents, wind and the dominating water. Wind can act all the way from the top of the highest mountains all the way down to sea level, and where it causes depositional accumulation, such sediments are called aeolian deposits, which are characteristically well-sorted, sand-sized, or smaller mineral grains. Not so for water. As glaciers and snow melt, they feed streams. Together, glaciers and streams do the most geomorphic work on Earth, that is, shaping of the Earth's surface. As streams move eroded pieces down out of the highlands, they round them and deposit moderately to poorly sorted conglomerates to start with in the headwaters of the stream. At the base of mountains, hill slopes, and in down-dropped basins, the deposits that appear to be water-eroded but not dominated by main river systems are called alluvium, or alluvial deposits. A special environment involving alluvium is the base of steep mountains where energy levels suddenly drop, and these are called alluvial fans. Such fans are dominated by braided streams due to having more sediment supply than the streams can usually transport, a common feature of alluvium. The largest, most angular clasts, rock fragments, are near the mountain source, and the smaller and rounder clasts deposit further and further from the mountain face. But don't think the stream spreads out in all directions simultaneously to make this fan shape. This is sediment-dominated, not water-dominated. One shallow, wide stream track is taken for a time, depositing eroded material from the nearby highlands until the stream's steepness lowers and another steeper route is taken. If you could see an alluvial fan through time, you would see the stream jumping from location to location, slowly building upward and outward. Ephemeral flows join together downstream to form environments that become more and more water-dominated, with two main flavors on land, rivers and lakes. The further downstream clasts are eroded, the smaller and rounder and better sorted the clasts get. So we start to get coarser material in the fast-moving stream channel, often sand-sized or smaller, but occasionally better sorted conglomerates. The edges of the stream are called floodplains and are normally exposed to air, but going underwater and becoming more depositional during floods. Floodplains usually get the finer silts to mud settling out of this more stagnant water that has left the faster-moving stream channel. Together, the channel and the floodplain deposits of river systems are called fluvium, or fluvial deposits. Coarse sediments, which are not laterally continuous, often containing crossbeds, surrounded by finer grain muds, both of which may contain terrestrial fossils, meaning fossils of organisms that lived on land, all point to a river or fluvial environment. Whether in the headwaters or downstream, we meet lakes and swamps with still, stagnant, or standing water. With a greatly reduced energy level, we see coarser fluvial sediments at the shore, but the interior is dominated by finely layered clays and silts, and even evaporites or other chemical precipitates can form. Lacustrine is the term for lake deposits in general, but when deposited in a repeated, rhythmic pattern, we call those deposits varves. The Castile Formation's environment 250 million years ago was actually a lake formed near the shore of an ancient ocean but dammed by an extinct coral reef. When the conditions were arid, this closed basin evaporated and deposited evaporites of mostly halite and anhydrite. But during more humid conditions, seawater could leak through the reef, replenishing the lake with nutrients so that plankton grew and died and formed carbonates. And if enough runoff could make it into the basin, silt and clay deposited. The general rule for carbonates is they can only dominate an area if the clastic supply is low to none. Just a little mud will overwhelm carbonate production and make a mudstone, though perhaps a calcitic mudstone. Pollen can be thought of as a clastic particle which gets incorporated into sediments in lakes, and looking at pollen, which can often be identified to the species level within these annual varves in lakes, gives us wonderfully detailed information about the changing ecosystems surrounding such lakes through time. The study of pollen in such sedimentary deposits is called palynology, and the study of inland waters in general and their interactions with the rest of the environment is called limnology. Lakes are often dammed, and dams can break and cause flooding. Well, no matter their cause, flood deposits are less well sorted and often have larger class sizes. I say often because it depends on what material is available for the flooding waters. Glacial outwash could be lumped as a special case of these overly energetic water deposits, and flood deposits in general can be lumped as a special category of fluvial deposits. But more often the streams leaving a lake are at typical flow, where we get these mixed sediment sizes in fluvial deposits we previously discussed, which persist down to the beaches of the world. All along the way there are soil deposits, which develop mudstones, and we mean mudstone and not shale, as the plate silicate minerals are not lined up. With water saturating the lower part of a soil stack, oxygen tends to deplete there. But above the saturated portion of the soil, air keeps the oxygen levels high enough to change the basic chemistry of one of the most common elements on Earth, iron. With no oxygen, iron becomes chemically reduced and we call it ferrous iron, which tends to display green to gray colors in rocks. With oxygen present, iron is oxidized to ferric iron, which tends to display yellow to red colors. Mudstones with brightly colored greens and reds are most likely to be ancient soil deposits, which we call paleosols. But land gives way to water at the beaches of the world, and there we get a range of particles depending on the average energy at the beach and the source material, but overall tend to be well sorted, with the rolling motion at the beach rounding larger clasts. Of course, most beaches accumulate sand, but very well sorted is the general rule, and beach deposits extend laterally much farther than the stream deposits. Terrestrial fossils transition to marine species at the beach, or even more specific beach species such as certain crabs, starfish, and coastal plants. Like the alluvial fans, as a river goes from a constrained land channel into a still body of water like a lake or the sea, it will deposit a feature called a delta, named after the sediment deposit at the mouth of the Nile River, which looked to ancients like the capital Greek letter delta. But there are various types of deltas which can be classified as wave-dominated, tide-dominated, or even fluvial, river-dominated. The Ganges and Brahmaputra rivers join to form a delta that is tide-dominated, with less wave action. The Nile Delta is wave-dominated with less tidal action, and the Mississippi Birdfoot Delta is a fluvial-dominated delta as the Mississippi River discharges about a ton of sediment per second onto its delta, and the Gulf of Mexico is relatively low in both waves and tides. Deltaic deposits are usually fine-grained, mostly mud, with various bed features such as the bottom set beds, foreset beds depositing off of horizontal, and top set beds on top. Evaporites show up again at beaches, appearing first above the high tide line in sabkhas, which will have carbonates, evaporites, and some silt to fine sand. Otherwise, evaporites are more common along hotter, drier shorelines and where bays can get cut off and evaporate faster than the water input. If the bays are sheltered and have enough water and nutrients, limestone can also accumulate. But as we noted before, limestone formation requires little to no clastic input, thus our specifying sheltered bays. No rivers run in from the shore side, and reefs often protect from the high-energy ocean waves. Limestone in the sheltered bay makes uniform, usually micritic, sometimes oolitic, limestone layers leading out to the protective reef where the rock becomes coquina, the limestone made of skeletal fragments of reef builders. Brecciated, that is, angular, broken up skeletal fragments from the reef find their way offshore into deeper waters. But if the shore is unprotected from clastic input, the classic form is to have sand at the beach, which is much more uniform and laterally continuous than fluvial sand deposits, and contains fossils of beach-loving species. As we move offshore, we get the smaller silts settling out, and then the clays even farther out. Silts and clays show up in aeolian, fluvial, and lacustrine systems as well, but none of those extend quite as far as the marine silts and shales. And the iron in these deep water deposits is more likely to be reduced than oxidized. The dinosaur Cretaceous-aged Pier Shale on the Colorado School of Mines campus contains marine fossils and can be mapped across the North American continent, larger than any river floodplain or lake could make. Just the size tells us there was an intercontinental sea through the middle of our continent in the Cretaceous. With a repeated reminder that limestone forms where there is little to no clastic input, it should be no surprise that if we can get out past the beach where the sands get removed, past the near-shore silts and the offshore clays, we can finally get to where the calcite planktonic skeletons can be the dominant clastic particle settling to the sea floor, and we see the deep marine limestone forming. In Dallas, where I grew up dreaming of being a geologist, the rock in the nearby creek bed was Cretaceous-aged Austin chalk limestone with marine fossils. I was hunting for dinosaurs in the right age rocks, just not the right environment. This limestone tells me in the deeper parts of the intercontinental sea, limestone formed. There is a catch here, though. Calcite dissolves better in colder, higher pressure water, which is exactly what we find in deeper oceans. Thus, when we get down to about 4,200 to 4,500 meters depth, calcite begins to dissolve faster than it precipitates, and no calcite and thus no limestone gets preserved. Below this depth, called the carbonate compensation depth, or CCD, calcite does not accumulate, and so even with very low clastic input, wind-blown silt and clays and insoluble organics are the only things to settle into the deeper seas at very, very slow rates. But there is one more dramatic sedimentary deposit that can occur in these deep marine settings. The submarine fans of coarser material and often including graded bed turbidites from higher energy density currents moving sediment down into these deeper waters. Though turbidites can also occur in lacustrine, lake environments, they are more likely marine and often deep marine where the continental slope breaks into the abyssal plain of the seafloor. The presence or absence of calcite can be a clue to just how deep these deposits were. And speaking of the solubility of calcite, it should be no surprise to see buried and pressured limestone take on stylolites, the result of dissolution we met in the secondary sedimentary structures. But with that, we are seeing the first changes of rock in the solid state. When we come back next time, we will start our investigation of the last rock type, the metamorphic, or changed form rocks, which have been altered physically and or chemically in the solid state. We're going deep next time to meet these mysterious information bombs, here on Earth Explorations.